Alright guys, this video is going to be a Unit 6 review day video. We're going to talk about what functions are and identifying if a certain relation is a function or not. I'm not going to graph a piecewise function just because that takes a little bit of time. If you want to see a video on graphing piecewise functions, check out my Unit 6 video, which I'll provide a link for you guys, but you should be able to find it. Additionally, I'm going to go the other way though. I'm going to go through coming up with the equation of a piecewise function. We're going to talk about average rate of change, operations on functions, so adding or subtracting or dividing, all that fun stuff. We're going to compose functions together using composition notation. We'll also talk about inverses in this video, what an inverse is, and how we can algebraically find it. So starting back from the top, a relation in which every element of the domain is paired with one and only one element of the range is the definition of a function. What this means is every x value has only one y value. Okay, so your x's aren't going to repeat. The graph of the equation needs to always pass the vertical line test. So your domain, again, is your x's, your range are your y's. So a function that looks like this, we'll say this is like y equals x squared plus 1. That's a function, because if I were to draw a vertical line through at any location, it's only going to hit the graph once. Now, a graph like, let's say x equals y squared, is a sideways parabola. If I draw a vertical line, see how it's hitting the parabola at 2 points? Therefore, this is not a function. So this is a function, this one's not a function. This is just a relation, okay? So like I said, by definition, every x has one and only one y. As we're over here, you're seeing an x value having actually two y's. So based on that, your x's can't repeat. So if you look at this set of points, see how b, which is an x value, repeats? This tells me that this is not a function. Okay, the picture right below, this looks like a square root function that's been reflected in the x-axis. It passes the vertical line test, so this is a function. In this unit, we talked about piecewise functions, which are basically pieces of functions put together. So in this case, I'm seeing a parabola, a point, and a horizontal line. From left to right, this is your basic y equals x squared parabola. And I can tell because 1 squared is 1, 2 squared is 4, negative 3 squared is 9, and so forth, okay? So I'm going to be from left to right, first the function x squared, but on the interval where x is less than, it looks like 2. Okay, so from negative infinity up until 2, you're going to be the function. But notice how I use this set notation. I didn't use parentheses. I didn't use interval notation to say that. Okay, then I'm going to be 1 when x equals 2. That's the 0.21, right? So you're going to be the y value of 1 when x equals 2. And then I'm going to be the line y equals 4 when x is greater than 2. Now, something I didn't talk a lot about, notice how there was an open circle here for that parabola as well as the horizontal line. That's why I said less than 2 as opposed to less than or equal to 2. That would not be correct, because that would mean, whoops, that would mean a closed circle and it's opened. Alright, the next thing we talked about in this unit was average rate of change, which is calculated by your basic slope formulas. So change in y over change in x y2 minus y1 over x2 minus x1, or just your basic rise over run calculations. So typically how we ask this is we give you functions and they're shown in different ways. Like this is just an equation, this is a table, this is a graph, and we're going to compare their average rate of change over specific intervals. This is the part that's really important. A lot of people overlook that. Okay, so like when I look at the table, I'm literally going to highlight x equals 1 and x equals 3 because that's my interval. A lot of students will ignore the interval and do the whole table. We don't want that. Okay? So I actually start with the table. When I'm calculating the average rate of change, it's going to be 54 minus 6 over 3 minus 2. So 3 minus 2 is 1. 54 minus 6 is 48. So my average rate of change is 48. Wait a minute. Whoopsies. I made a mistake. Just in the bottom part, though. It was 3 minus 1. Okay, and then 48 divided by 2 is 24. Sorry about that. Okay, so my average rate of change is 24. Over here on the graph, I'll pick out the values. So at x equals 1, we're at 3.25. At x equals 3, it looks like we're up here at 9. Okay, so I do 9 minus 3.25 over 3 minus 1. Again, this was the coordinate 3, 9. Denominator's 2. 9 minus 3 is 6, but take away another 0.5 would be 5.75. So 5.75 divided by 2. Oh, jeez. Okay. Okay, so 2.875. Okay, so that's one average rate of change. And lastly, a couple things you could do. You could either evaluate the function at the values you need, which I tend to do only because I think I'm faster this way. So I get 9. 15 plus 4 is 19. Okay, so you have the coordinates 1, 9 and 3, 19, and then do the slope with that. Another thing you could do is plug this into the y equals in your calculator and look at a table. Like I said, I think I'm faster evaluating it, but if you're worried you're going to make a mistake, you can do that as well. So from there, I've got 19 minus 9 over 3 minus 1, 10 over 2, which is 5. So the question is, which has the greatest average rate of change? So the greatest would be the largest number, right? So I'm comparing these values. F of x is the largest. Who has the smallest? 2.875, so that would be h of x. Done. And this typically shows up as like a 4-point question on a Regents exam, so really good to know. All right, notation for operations on functions. It's just like what it looks like. If you have f plus g of x, that means take f of x and add it to g of x. F minus g of x, take f of x, take away g of x. This looks like I had a little bit of a translation error, but if I had to guess, this is f times g of x. Sometimes math print doesn't work on my computer at home. All right, so this would be f of x times g of x, and lastly, f of x divided by g of x. Okay, keep in mind when you add, subtract, or multiply functions, the domain doesn't change, and it will take on any restrictions that the original functions have before adding together. When you divide functions, though, you need to recalculate. And what that means is you need to look for where it's undefined. Okay, so I'll go to the next page. So I'm actually going to skip ahead to D right now, just talking about that note. See how I have k of x divided by f of x? k of x is this parabola. F of x is this line. Okay, now separately, the domain of a parabola is all reals, right? The domain of a line is also all reals. So separately, they have no restrictions, but when you put them together, this denominator can become 0. So you need to say, well, I have a restriction here. If I set this equal to 0 and solve for x, x would be 5/3. So what that tells me is the domain of k of x divided by f of x is all reals, except x cannot equal 5/3, because if you plug it in, that would cause your denominator to go to 0. Okay? G of x, its domain, if you were to look at a graph of this, it's a square root function that's been shifted left 1 unit, vertically stretched by 2. So the domain of that guy is from -1 to infinity. Okay, so when I subtract f and g of x, I have 3x minus 5 take away 2 times the square root of x plus 1. My domain, when I compare all reals and this restriction, it'll take on the restriction. So that means when I add these together, I can't have any values less than -1. One thing I skipped over was a, g plus f of 10. You'd evaluate the function g at 10, get a value. Evaluate f at 10, get a value, and then you just add those together. That's not too crazy. All right, composition notation. This is kind of new for us. It's always read backwards. Nested notation, same idea, read backwards. You'll do whatever's inside the parentheses first or whatever's furthest to the right first. So when I see f of g of 2, I'm going to calculate g of 2 first. So 2 squared minus 3 by plugging in. 4 minus 3 is 1. Now I'm going to take this 1 and plug it in to now f of x. Okay, which is what it wants me to do here because of reading it backwards. So I've got 1 plus 1, which is then 2. So this is your final answer. Okay, now it's not commutative, meaning you can't just switch the order and get the same answer. I'm going to calculate f of 2, which is 2 plus 1, which is 3, which means I'm now going to calculate g of 3. So 3 squared minus 3, which is 9 minus 3, which is 6. That's your final answer. So notice you don't get the same thing. Okay, now this one's a little bit trickier. What this says is you're going to take f of x and plug it in to g of x. So I'll show this a couple ways. G of x is x squared minus 3, right? So you're going to take x squared minus 3 and plug it in to f. So that means everywhere I see an x in f of x, I'm going to rewrite it as x squared minus 3. So my result is x squared minus 2. Okay, so that's one way of thinking about it. Another way I tend to write it as well is I'm taking g of x and plugging it into f of x, right? So sometimes I'll write down f of x first. And then I remind myself, if I'm plugging g of x into that, everywhere I see an x, I'm going to replace it with g of x. What's g of x? X squared minus 3. Either way, you get the same answer. Inverses of functions is anytime you take a function and reflect it over the line y equals x. So that's a line with a slope of 1 going through the origin. Okay, so if you have a function y equals x squared plus 3, we'll essentially switch the x and y coordinates, and that's what will reflect it over the line y equals x. All right, so for example, on the interval of 0 to 3, my original function, x squared plus 3, would be, let's see, 0 squared plus 3 is 3, 1 squared plus 1 is, or 3 is 4. Okay, those would be my values. Actually, this is a 12. All right, there we go. So let me just graph that portion. So 0, 3. Actually, the 3 would go off the graph. It would look something like this. So it's half of a parabola, essentially. I graphed the right half of it. If I want the inverse of this function, which again is just reflecting over the line y equals x, which is kind of lightly dashed in here, we'll just switch our x's and y's. And then I'll graph. And there you have it. Okay, now the reason I restricted this domain, meaning I only did from 0 to 3 to start, actually I probably should have ended this. Actually, never mind. We're okay. My whole point was that since it wanted me to graph from 0 to 3, but I couldn't fit that third coordinate, I really should end it at 312, wherever that is, so somewhere up here. Same thing over here. Okay, really it's just a portion of it. It's not continuing with an arrow. Okay, anyway, so the reason I restricted this function to just a little bit is because imagine what would happen if the other half of the parabola existed. Then the other half of the parabola exist over here, and then that doesn't pass the vertical line test. So in order to keep it being a function, I restricted the original function in order to keep the inverse being a function. Okay? Now, algebraically, when you solve for inverses, it's the same logic. You switch x and y, okay? So in order to do this, we switch x and y, and we solve for y. So for this first guy, remember f of x is just a fancy way of saying y. I'm going to switch x and y. And now your objective is to solve for y. So I'll undo the third root with the cube root. And subtract 4. Now keep in mind, it's not y, it's f inverse of x. We just called it y to help us solve. And we're done. Okay, that's your inverse. It works going the other way too. In question B, I gave you the inverse, and I want the original. I'm still going to think of this as y, and switch x and y. Now this one's going to be a little bit tougher, so let's make sure we pay attention here. I have 2 y's. I need to solve for 1 y. So right now I'm going to get rid of the fraction by cross multiplying. Okay, I'm going to distribute. Now your objective is to get the y's together on one side of the equation. So I'm going to subtract the y over, and I'll move the 2x over to the other side as well. I can factor out a GCF of y. That allows me to get 1y. And then I just need to divide by x minus 1. And then we're done. Okay, so remember you started with the inverse when we wanted the original. So that means f of x is equal to negative 2x minus 2 all over x minus 1. And we're done. Okay, last thing I'm going to do in this video is talk about how you verify inverses. In order to do this, you use compositions. Okay, so that means we're going to do f of g of x and g of f of x. And we need to show in both scenarios they equal x. Alright, so from part A, let's call the original function f of x. So it was x plus 4 cubed. G of x I'll use as my inverse. So that was the cube root of x minus 4. Okay, so let's first do f of g of x. So that means I'm taking g of x, plugging it in for x in the function f. Okay, I'm just going to highlight for you so you see this. This right here, that's g of x, which I've subbed in for x. Then I had to tack on the plus 4 because that's the rest of the f function. All right, let's simplify. 4's will cancel. Cube root of x cubed is just x, so we got it to work one way. Now we got to do it the other way. So I'm going to take f of x, okay, which is this guy, and plug him in for g of x. Okay, so this will be the cube root of, now remember this x is now going to be x plus 4 cubed minus 4. So again, here's that substitution you guys are seeing. X plus 4 in for x. There's x plus 4. Clean this up. These will undo each other. And then when I simplify, it goes to x. So therefore, they are inverses.